Good afternoon, good evening, friends. Pleasure to have today's speaker with us, Dr. Roya Mohayaee. She's Director of Research at CNRS at Sorbonne University in Paris. Roya did her PhD at Imperial College London in 1995 in the area of string theory, but subsequently she switched to cosmology while doing postdocs at Trieste, Sao Paulo, Rome, Côte d'Azur, and Cardiff. She became a faculty member at Institut d'Astrophysics Paris in 2006. Roya has made seminal contributions to the theoretical understanding of large-scale structure formation in the universe using techniques such as Monge-Ampere gravity and optimal transport. She has also been involved in analyzing observational data, for example, to reconstruct our local bulk flow and baryon acoustic oscillations. In recent years, her focus has been on testing the cosmological principle, which underpins the standard cosmological model. And today we'll hear from her on this related matter, challenges to the standard model of cosmology, the cosmic dipole anomaly. Over to you. Pleasure to have you with us.
Thank you very much. Thank you for that introduction, and thank you for inviting me to give this talk. So let me share. Is that? No, it's this one. I have to have the right. Just check. Yeah. Okay, so I'll be telling you about challenges to the standard model of cosmology, and in particular to the problem of the cosmic dipole anomaly. Now, this is the work that I've been actually doing with Subir and his various postdocs for the last, now it's 15 years, more than 15 years now. And these are the different people who have been involved. So I already apologize to Subir and to a few others who know all about this. So I hope it's not too boring for you. So what is the standard model of cosmology? Because many of you are particle physicists, I just want to make a little comparison between our two standard models, the standard model of particle physics and that of cosmology. Just want to start with that. So standard model of particle physics is, of course, at much smaller scale. Standard model cosmology explains the phenomena on much larger scales. Standard model particle physics based on quantum field theory, gauge symmetries. Standard model cosmology, on the other hand, is basically using gravity, the only force that we consider in cosmology. And it's not just general relativity, it's really using Friedmann-Lemaitre-Robertson-Walker metric. And not only that, it is using a special combination of parameters and growth rate. It's a 6-parameter model that is called lambda CDM. So again, the standard model of particle physics is basically based on the particles that have been detected, has been predicted by this model, the quarks, leptons, photons, WZ bosons, and gluons. The standard model of cosmology, it's based basically on lambda, on the assumption of lambda and the cold dark matter. That is why it's called lambda CDM. Now, here we come to lambda. So there's prediction from the quantum field theory. A lambda in particle physics is the vacuum energy. You can calculate it using quantum field theory. And in cosmology, lambda is the cosmological constant that rises, you can put in Einstein equation. And if you calculate that from quantum field theory and compare it to the lambda basically related or derived from observations, then you see that there's a huge difference in the value of this parameter. This is, I think you agree with me that this is one of the biggest challenges and problems of theoretical physics, today. So standard model of particle physics has been tested to a high precision. Standard model of cosmology is very much phenomenological. It fits the data quite well, the model of lambda CDM. And if I may say, standard model of particle physics is fundamental, whereas standard model of cosmology is very much descriptive, is phenomenological, and is founded on CP, and CP is not charge parity, is cosmological principle. So a standard model of cosmology is based, lambda CDM is based on the cosmological principle. So what is cosmological principle? Is really the cornerstone, is the foundation of lambda CDM. And what it says is that it assumes, it's an assumption, that the universe is homogeneous and isotropic on large scales. So for you, theorists and physicists, homogeneous and isotropic basically means that your metric is invariant on the translation and rotation. So if I write such a metric, it's basically the FLRW metric. It's got a single parameter A of t, it's a scale factor here as you see, and it just depends on time. Now the universe doesn't have to follow our philosophy of simplicity. The universe doesn't have to be homogeneous and isotropic. So it can be actually homogeneous, but not isotropic. In this case, the universe will have an axis, a preferred direction, and the metrics then would have to change. It cannot be simply a one single scale factor. You can have different scale factor depending on the direction. An example of such metric is the Bianchi models, Bianchi metrics. Again, the nature doesn't have to be homogeneous and isotropic. It can be inhomogeneous and isotropic. In this case, the universe would have a center, a preferred center, preferred observer. And example of such models are the Lemaitre-Tolman-Bondy models, that in which case you see that the scale factor, you have got one for the angular directions and one for the radial direction. And so it's very different from FLRW metric. Now the universe could be much more complex. It could be neither homogeneous nor isotropic. And in that case, you have a metric that is a lot more complicated. And in that case, the example of such metrics is metrics that are given by Sekeres model. So you see that the metric, as soon as you go away from FLRW, the life becomes quite complicated and not practical. And in fact, if you go back, when Einstein wrote his equation in 1915, he was looking for solution. There is a very difficult 10 equations and highly nonlinear. So they wanted to solve it. So he came up with a simple metric in Einstein model in which he had a matter and a cosmological constant because he didn't want the universe to expand. This is prior to the Hubble, So he wanted to sort of buffer the expansion of the universe. He introduced cosmological constant, and Einstein model, then people found that it's not stable. So then de Sitter came, and de Sitter actually removed the matter, and he said, okay, there is only cosmological constant, the universe is static, and then, voila, that was de Sitter model. Now here comes the power of theory. There came Friedman and Lemaitre, and this is well before Hubble, and well before the observation. Friedman said, well, why do I not say the universe is expanding? Let's put the expansion there. Let's not try to suppress it. And so he proposed a metric, and actually this was opposed by Einstein at the time, but then later on it became accepted as the expansion of the universe was found later on. And Lemaitre actually was more or less the same time. And Robertson and Walker were just mathematicians, basically, who showed the rigorousness and of the metric, and that this was the only maximally symmetric metric that one could write for Einstein equation. Then came the discovery by Hubble. So now Einstein and de Sitter, they came back to the Einstein equation, and so they proposed a metric. They accepted the expansion of the universe, and that was Einstein-de Sitter universe. Now we know that Einstein-de Sitter universe and de Sitter universe are basically two limits of FLRW metric. when you go to very early times, the universe is basically Einstein de Sitter, and if the universe is now FLRW metric, then when you go very far into the future, it becomes de Sitter universe. Now, these guys were trying to basically solve Einstein equation, and of course, when you have a very difficult equation, you first try to find the simplest solution to it. You don't start with a very difficult metric with a very difficult solution. This is quite usual. This is how we actually work. But they didn't have a philosophy that the universe had to be homogeneous and isotropic. And this was actually proposed later on by Milne. Milne, who was a professor of mathematics in Oxford, he actually was the first person who talked about cosmological principle. He had a model that Milne universe, which is like an open universe. It doesn't have general relativity in it. It's just based totally on special relativity. And the best account of Milne cosmological principle is really given by Paul Dirac in 1937. So Paul Dirac writes this very nice account of Milne's model that, we now feel the need for some new assumption on which, I cannot see my, okay, on which to build up a theory of cosmology. This need is partially satisfied by the assumption which Milne calls the cosmological principle. Now, then Dirac goes on, and this is very, very interesting. He says that apart from local irregularities, the universe is everywhere uniform and has a spherical symmetry in 3 dimensions. These assumptions are fairly plausible and have a great simplifying effect on the subject. And until there is more definite evidence of their inadequacy, it does not seem worthwhile to try more complicated schemes. So this is the cosmological principle. You can consider it like a religion on which you are going to build your science. So we are not in 1937 anymore. I've somehow lost, okay. And this cosmological principle actually became a big subject of debate at that time. And Karl Popper, who was a very prominent philosopher, he still is considered as a very prominent philosopher and historian of science, he actually wrote at that time, was very much against the cosmological principle. He considered it quite dogmatic because he believed that a scientific theory has to be falsifiable. And he said, well, cosmological principle, I cannot falsify it. But we are not in 1930s anymore, and we can actually see if we can falsify cosmological principle or not, because we have got very many observations now. We send satellites into space, we have huge telescopes, we spend billions and billions of pounds on building these instruments. So we don't have to believe in cosmological principle, we don't have to consider it as a religion or as a faith. We can just go and figure it out using observations. And the very first observation, I don't know if it's first, but the very strong observation in support of the cosmological principle is actually the cosmic microwave background radiation. So this is a radiation coming from the very, very early universe, from the universe was actually born. And here you see the fluctuation in the temperature. These reds and blue are basically the differences in the temperature that were measured using, if you like, thermometers, in this case bolometers, putting in different part of the space, and they're measuring the temperature, very, very cold temperature, few Kelvin temperature. And these little dots are basically fluctuations. The difference between the red and the blue is 10 to the minus 5 Kelvin. So it's tiny. So you can consider the universe to be isotropic, to be homogeneous, no matter where you look. Because this temperature anisotropy is just so tiny. However, we haven't got to this map when we took the temperature, when we went around and measured it with different telescopes, if you like. The first map that you get when you put your thermometer or your bolometer to measure this temperature is actually a 100 times larger fluctuation. There's a fluctuation that is basically covering this primordial fluctuation, which is 100 times larger. It's called CMB dipole anisotropy. Now, because it's 100 times larger, people from the very beginning attributed to have a different origin from the CMB primordial fluctuations. And although the CMB primordial fluctuations go back, have fundamental origin, fluctuation in the coming from inflation, if you like, or other origins, this dipole anisotropy of CMB was not considered to be fundamental, to have a fundamental origin. And it was attributed completely to our motion. So the motion of the observer. Because we are an observer, and because we have a motion, now with respect to what? With respect to rest frame given by the primordial CMB fluctuations, and that will become clear a little bit later on here what that reference is, then our motion will produce a dipole. So CMB fluctuations are considered to be a black body, and an observer that moves in a black body radiation will see a dipole, and that dipole correspond to this. And from measuring this dipole in the temperature, we can deduce the observer's velocity. And this is the work that was done by Jim Peebles and David Wilkinson very early on, more or less the same time as the discovery of the cosmic microwave background radiation. Now, if the universe, you would ask, if the universe is homogeneous and isotropic, then why do we move? Why do we have a motion? If we have a motion, there is a direction. That means it's not isotropic at least. We are going somewhere, so there is a preferred direction. So what is the origin of this CMB dipole? Now, this is quite interesting because it goes back to what Dirac said, actually. He had a vision. He talked about these irregularities. So he was talking about these fluctuations locally, you see. Also, the universe on very large scale is considered by cosmological principle to be homogeneous and isotropic, but it allows for local, if I may say, fluctuations in our neighborhood. So if you consider us, actually, we are here, looking, MW means Milky Way, this is our galaxy, and this is the largest cluster near us, this is Virgo cluster. And we have known for a long time that we are moving towards this Virgo cluster, not only us, all these other galaxies, these tiny galaxies, are moving towards Virgo. There is a Virgo-centric info. So there's a direction, we are going to that direction. Now, is Virgo responsible for our motion? Is Virgo giving the motion that is predicted from the dipole anisotropy of the cosmic microwave background radiation? And it's very interesting because even before the calculation done by Peebles and Wilkinson, Dennis Sharma actually predicted a CMB dipole by looking at our motion towards Virgo, basically. So he said, because we are moving towards Virgo, because there's this Virgo-centric info, then I predict that there should be a dipole anisotropy in CMB. So this is before calculation of Peebles and Wilkinson using black body radiation. But is Virgo really, pull of the Virgo is enough to explain the CMB dipole or not? So this is what it was thought at the time of Sharma, but later on, people have looked at the universe far and far away from Virgo. Now we could map the universe away from Virgo. This is about looking at distances twice as large away from us than Virgo is. And here you have got another two huge clusters. They are called Hydra and Centaurus. Otherwise, they are known as great attractor. And then people came and said, oh, no, Virgo cannot explain the CMB dipole completely. You also need to go all the way to great attractors at about 50 megaparsec. So this was put forward also by Taman and Sandage. Okay, Virgo cannot explain it. You have to go to great attractor. You have to go far away. Until Lindenbell, who was always ahead of his time, came and said, well, I don't think so. Great attractor and Virgo, they're not enough to explain the origin of the CMB dipole. And then there came this paper that became very well known as the paper of Seven Samurai, and showing exactly that, in fact, you need to go beyond great attractor to explain the origin of the CMB dipole. So how can we know where the origin of this dipole is? What is the state of the art now? Because when I showed you the Seven Samurai paper is 1987, and since then we had many observations. And here I'm going to look at, to answer this question, what is the origin of CMB dipole? I'm going to look at three types of observations. In cosmology, astronomy, when you observe, basically you can categorize your observations of larger scale into three classes. So first class of observations are fantastic. They look at sources in the sky and they give you almost every single information that you need. They give you the angular position of the source. They give you the radial position, which is the redshift, but the redshift is not the distance to the source. These observations, they also give you the distance to the source. Now, there are not very many data when you want all of these four information. There are a few thousands. And typically, this is the data that comes from supernovae. Supernovae are considered standard candles. They give us the angular, radial, and the distance position of the supernovae, of the sources. Now, if I have all of these informations, then I can do what Seven Samurai, what Lindenbell, what others have done, and I can see how far I have to go to reach, to explain the CMB dipole. And this is the work, actually, I started working with Subir with this work on supernovae. We were looking to see whether we could find any anisotropy in the acceleration. We did not find it at that time. We found it about 12 years later using better data. But at that time, we didn't find, because the data was not good enough. It was like about 700 supernovae. We found something else, which was interesting, very interesting, that we looked at different cuts in redshifts, and we tried to find if we could converge to CMB dipole or not. Here are different cuts. You see, first I have Virgo. This is what Denis Sharma thought was the origin of the CMB dipole. I have now great attractor. This is what Taman and Sandage thought was the origin of the CMB dipole. And then I can go further away. And now I'm measuring, basically, this is slightly different from our motion, but this is a motion of a whole group of galaxies, which is related, gives us the convergence to the standard frame of rest. And so then you add more and more, because now we have got better data. So our data is much better than the time where the Seven Samurai, they wrote their papers. So we add more and more. And you see, we are seeing, and what do we want to see if the standard model of cosmology is correct? We want to see this blue curve, and we are at 1 or 2 sigma. The statistical significance is not very large. What it's showing is that I'm not really converging to the CMB dipole. Within 2 sigma, maybe I am, but it's just quite questionable whether I am converging or not. You can say, within 2 sigma, I agree with lambda CDM. You can say within 2 sigma, I disagree with lambda CDM. So can I do better? To do better, to have a better statistic, you need more data. If you want more data, then you have to compromise on the information that you'll get. And the second bunch of data we have, and which give us information for millions of sources, let me remind you that the first bunch we had, like supernovae, they gave information for about thousands of sources. Now I want to have information for millions. I want to increase my statistics. So this is second bunch of data. They are called redshift catalogs. They basically give me the angular position of the sources and the redshift. Redshifts are not distances. They're different. To go from redshift to distance, we need to assume a model, and I will come back to it later. So this is another work that I did actually with a student of mine. So you see here, you are looking at just positions and redshifts. What you're doing, you're assuming a model to get distances, and then you are doing a consistency check. And now you see that I have a lot more sources. And you see this was the Virgocentric infall of Shama, then later on infall towards Great Attractor. And now we've got this very important supercluster, which is Shapley. And now most of the people thought that, if you go all the way to Shapley, all of these structures that are more or less aligned in that direction, they can explain the CMB dipole. And do they? So this is the CMB dipole. This is the data, basically, is telling me, yes, I am converging, but then, not really. And this is the prediction of lambda CDM. This is 2 sigma from lambda CDM, and this is the data, and this is where I should be if I have basically converged to the CMB dipole. It's not clear, right? I mean, you could be converging, you could not be converging. It's very unclear, and the data is not good enough when you go above 100 megaparsec. So this has been a subject of debate because, as you see, it's very unconclusive. So these are different works. This is the work, C11 is the work that we did with Subir on the supernova that I've shown you. And this is the latest data. Look, this is what the lambda CDM is saying, this shaded part. And this is these points with arrow bars are basically the data, right? So the data that is coming very recently from a paper by Brent Tully and his colleagues using the Cosmic Flow 4 catalog is showing that we are far above it. I mean, this is not converging. There is no convergence. It's extremely unconclusive. Also, I've shown you that we are going far and far away. We've started from Virgo, then Great Attractor, then Shapley, but we are still local as compared to a huge scale, as compared to the scale of CMB. We are still local. You see, here where we are at best, basically at about 150, 200 megaparsec. CMB is very, very 1,000, at redshift of 1,000 at gigaparsecs. It would be very nice to see what's going on here. We don't really have much data. So, at such large redshift, we don't really see very many galaxies. What we see, we don't really see them because they are no longer in the optical bands, are basically radio sources, are basically quasars, infrared sources that are very luminous, that come basically from the center of galaxy. They are AGNs, they are active galactic nuclei. They are very, very luminous. These are the sources we have. So can we use these sources to find the origin of the CMB dipole, to see what's happening to the universe at larger scale? We have realized that at smaller scale, the universe is very much anisotropic. Using locally, we haven't found where the crossover to isotropy is. So if I look very far away, maybe I can answer this question. So this is the third set of data. You see, the information decreases. Now I don't have a knowledge of redshift. I don't have a knowledge of distances, but I have loads and loads and loads of sources. I have millions of sources. But then how can I find out, just with this two knowledge of angular position of sources, how can I discover anything about the isotropy of the universe? How can I find anything about the rest frame of the CMB? Well, now I'm going to take a little detour. This is quite important to keep in mind that all this data that we are using very often in cosmology, they are analyzed using a background metric. So very often we are using a background metric to analyze data And then we are saying, okay, the data agrees with the model. Very often, this use of background metric is implicit. Sometimes it is very explicit. So one has to take very much care nowadays in cosmology. For example, when you have supernova data, of course, if you consider the distances, in observing the distances, you're not assuming any background. But very often you're comparing it to observation and you're using redshift to get distances. As soon as you go from redshift to distance, you have to assume a background. And this is what is done when people look at supernova data. So, assumption of background. Look at cosmic microwave background radiation. Of course, the temperature anisotropies, we are not assuming any background. But when you do the power spectrum analysis, you are actually, you have to assume an assumption on the metric. Baryonic acoustic oscillations, very much used to put constraint on dark energy, modified gravity, general relativity. You definitely need to use a metric, because as soon as you go from redshift or to a distance, you need to assume a metric. So then you use this, you put this metric to analyze your data, and then you're saying that data agrees with this metric. So it's circular. One has to be very careful. You can use consistency check, which is what most people are doing, but it's not the same as approaching data completely metric independent. It's very hard. Galaxy clustering, of course, you're assuming a metric. You have to, because you're using power spectrum, a 2-point correlation function, high point correlation function. You're going from redshift to distances. You need to assume a metric. Gravitational lensing, of course, because again, you're going from angles to distances. You need a metric. Now, all of these data and many more assume a metric. How can I check on the metric? You can do a consistency test. Sometimes people do that. But is there a nicer way, metric-independent way, of checking the metric, checking if the universe is isotropic and homogeneous as we want to, right? This is our task. We want to know whether the universe is isotropic. And you can do that. Now I'm going to show you the method that we have used is one of the very rare ones that doesn't have any assumption on the metric. It's a simple count of the sources. So this method actually is not new. It goes way back. It's one of the oldest methods in astronomy. And it goes back to James Bradley, who was a professor at Oxford. And he was actually looking at parallaxes. At that time, people were looking a lot at parallaxes of the stars. Parallaxes basically means that the position of the source changes according to the position of the observer. They were looking at that because the main reason was because of Copernican principle that, the Earth was moving. It was not the center of the world. We were not the center of the world according to Copernicus. And so people were looking to falsify that we were moving. So they were saying, okay, if we are moving, if I look at the position of the stars at two different positions of Earth, if Earth is moving around the sun, then I should see that there is a parallax. I should see that the position of the star has changed. It was very, very hard to measure parallax. It's a tiny effect. So Bradley was looking for that, but while looking for parallax, he found something else. He found something that was 100 times larger than parallax. He was finding an effect that seemed to be related not to the position of the observer, but to the velocity of the observer. And that was the aberration. So aberration was discovered by James Bradley, and that was aberration. So what is aberration? Basically, when you're moving, you're seeing sources at a certain angle because you have a motion. So you can see that simply when you're moving, like in a rainy day, you have to keep your umbrella at an angle. So this is basically aberration. You have got zillions of sources. You're at rest. Well, there is nothing, no effect to your seeing every single source. But suppose now you were moving. The observer was moving. Now I'm putting somebody running, but really it's the telescope that is moving on the Earth. then first thing is that you will see more sources because of aberration. In the direction of the motion, you see more sources here than behind. But there is a second thing. Not only you see more sources because you're moving, the frequency of the sources will change. So sources that are in front of you will be blue shifted because of Doppler effect, and sources that are behind you will be red shifted. So there are two effects. There is aberration of Bradley. You see the position of the star. Bradley was looking at the position of the star that is moving. And he could use this change in the position of stars to find the velocity of the observer. And actually, Bradley gave the best, at his time, measure of the velocity of light using this aberration effect. And there is a second effect, and that is Doppler boosting, which I showed you because the frequency changes. So if you're having a telescope, usually the telescope have a limit so they can see sources above a certain luminosity. Because the frequency changes, that would change the flux of the sources. So certain sources that you could not see, they would not be visible because you're moving, and certain that you could see, they would become fainter and they would move out of your telescope. Now, these two effects, Bradley's effect, when he did it, he didn't use a special relativity. As you see, the date, it was well before Einstein's special relativity. It was completely classical. And Doppler boosting, of course, was later, about 100 years later, Doppler effect. And Ellis and Baldwin in 1984, they put these two effects, not just for a single star, but for sources. This is what I'd shown you, for sources, you see, for many sources. So they put them together, saying that if I have aberration and Doppler boosting, the number of, there will be a dipolar effect. This is the dipole D I'm showing you here. And this dipole is related to our velocity. So if I could measure this dipole by simple number count the number of sources in front of you and behind you, then I can find the velocity of the observer. Then I can see if the velocity of the observer is the same as deduced from the CMB temperature dipole anisotropy. This is what we want, right? We want to find whether our velocity is the velocity given by the CMB dipole anisotropy or not. So let's use this. I'm not assuming any metric here. There is no assumption of metric. It's a simple number count. There are two parameters that enter here. You see X and alpha. Alpha is basically the spectral index. X is related to the count above a certain flux limit. I will show you. And these are measured at the flux limit. So if you measure it at flux limit, then you can approximate them very comfortably by a power law. Now, this was the paper by Ellis and Baldwin. It's very interesting to see. This is an extremely powerful, simple and very powerful test because major reason is because it's independent of the distance to the source. I don't need to know the distance to the source. I don't need to do the redshift. I don't need to do the distance. I can just use the angular position of the sources. It's really fantastic. So Ellis and Baldwin in 1984 paper, they say, thus existence of such an observed anisotropy is a test of the isotropy of the source count in the rest frame. The great power of this test is that the measurements can be made and the result must hold for any source counts, whether in a wide or a narrow solid angle, for flat or steep source spectra, etc., irrespective of selection effects or source evolution, as long as the forward and backward measurements are done in the identical manner. So this is what we then did. We applied this test to radio galaxies because the importance of this test is that you need to go very far. You need to go very far where there is no intrinsic anisotropy. And all the anisotropy that there is kinematic, that is due to our motion. Because if there was intrinsic anisotropy, as is the case for local universe, then you couldn't say all the anisotropy that I observe in the number count is due to my motion, right? So we have to go far where in the standard model of cosmology, the universe is supposed to be homogeneous, anisotropic, and then if I see an anisotropy, it's
Sorry,
due to
just
my
a
model.
question for clarification. So we assume that we are moving as indicated by the CMB dipole, and we predict what Ellis Baldwin effect that will produce, and we compare with data.
Exactly, that's what I'm going to show you.
Okay,
Yeah,
thank you.
you're ahead of me. Yeah. So here is what we have the data, and this is radio data. We've got about 500,000 radio galaxies. And so at that time, this is the work I did with Subir in 2015. And so we complemented this NOS, the catalog, this is MVSS catalog, with another catalog which was called SUMSS. So we had a full sky. But later on, I'll show you that you don't even need a full sky. So we had a full sky catalog, about 500,000 radio galaxies. This is the galactic plane that we cut, because there are a lot of nonsense in the galactic plane. And then we just measured, we just counted the number of the sources in different hemispheres here. This is one way of estimating our velocity. There are many other estimators. And so here you see, this is the number that I have in different hemispheres, and this is as a function of radius, and you see immediately a cosine. I'm not fitting really anything. This blue line is a data. So the data itself is giving me a cosine, it's giving me a dipole. It's just coming out of the data. And here you see, I compare it to the CMB dipole. So this is the radio dipole direction, the black circle here. And the green is the CMB dipole direction. And you see the directions are very similar. But now if I go and use the Ellis and Baldwin formula to get the velocity of the observer, you see that the velocity of the observer given by radio sources is more than twice that inferred from the CMB. Now, the problem is that this data, because we have got 500,000 sources, they have low statistical significance. So the statistical significance that we found at that time was less than 3 sigma. And this is actually said in the paper of Ellis and Baldwin that to have a statistically significant result, you need to go above 1 million sources. And this brings me to our latest catalog. This is the WISE catalog. Now, it's very different from MVSS catalog. MVSS was a ground-based telescope. This is a space. This is a satellite that people threw on the space. And so this is WISE. And here you have got millions and millions of sources. So you see WISE itself has scanned 700 million objects, but of course not all of them are galaxies, not all of them are quasars. We want quasars because we are sure that these are at cosmological distances at very high redshift. WISE observed these sources at 4 different frequencies. So you have that, this is WISE. Now if I just smooth the number of these sources, I'll immediately see some sort of a dipole. This was very encouraging for us. That's why we saw a dipole, you see, just by smoothing the density field. And then we went further to do analysis. This is the redshift distribution of these sources, of the WISE sources. You see, 90% of the sources, more than 90% are above redshift of 0.1, and many are above redshift of 1. This is what we want, right? We want to explore the universe at very high redshift. These are the 2 indices that I was telling you about. So there is X source count index, and the spectral index is alpha. And then what we did is that we made sort of mock catalog with all the specifics of these data, of the WISE data. So we put the same mask, we got the same alpha, we got the same X, and then we put an observer in that mock data that had a velocity as given by the CMB. And then we said, do we observe the same dipole or not? And we did this 10 million times, just to see whether this result was a statistical fluke or was really significant or not. And here you see, so 10 million simulations, this is exactly what we did. An observer moving with a velocity of CMB. Does it give me the dipole that I see in the quasar data? This is the dipole I see in the quasar data. This is the results of all these different simulations, and this is the CMB dipole. So this is at about 5 sigma away from what is given by the CMB dipole. The direction is not very far, about 20 degrees on the sky, but the amplitude is very far. And unlike the radio sources, this result has a very high statistical significance, above 4 and almost 5 sigma. Now, we went back to the radio data, and then we wanted to compare to see whether the radio data that I showed you, the MVSS data, and the infrared data agreed or not. We reanalyzed the radio data, and I show you the difference. So radio data is very different from the quasar data. These are completely different sources. Radio galaxies are evolved, red, dead, massive ellipticals. Quasars are different, are basically gas-rich disk galaxies coming from there. And these sources that we had in MVSS and quasars, WISE data, they are very little overlap, really tiny overlap, only 1%. And even that 1% we removed because we wanted to have completely independent catalogs. Different systematics, different sources, different observational strategies, different scanning patterns, everything different, two independent data. What do we find? So we have got that, see two independent data sets. And here is the data. Now I'm showing you the results slightly differently. Before I showed you amplitude and direction separately. Now I'm doing something that is very usual to do in cosmology, using the 1 and 2 sigma and 3 sigma and 4 sigma lines. So here we are plotting the dipole and the contour plot for the dipole and the offset from the CMB dipole, angular offset from the CMB. So we have got a CMB dipole direction, and we get it from our catalog. The left is the MVSS radio data, the right is the quasar data. And you see these are those simulations that we ran again. And here is the result for the radio data. These are the 1 and 2 sigma lines. And you see it is beyond 2 sigma, which is what we had found before. And here is the quasar data. So here we are being really, really conservative. We are only considering the amplitudes that are within certain offsets from the CMB direction. And you see this is, again, above 4 sigma. Now you can combine them properly, not just multiplying them, but combine them properly using proper statistical methods, and you get above 5 sigma. Now these data and the cause and everything, we made them from the beginning up to now available for the public. And so now what is happening? What can we deduce from that? So I go back to the paper by Ellis and Baldwin, because they already tell us if the CMB dipole and the matter dipole, they do not agree, what that implies. So, and here it is. If the standard of rest determined by the MBR, at that time they would not say CMB, they would call it microwave background radiation, then it changed to CMB, this is the same thing. So he says, if the standard of rest determined by the MBR and the number counts were to be in serious disagreement, one would have to abandon either A, the idea that the radio sources are at cosmological distances, because at that time people were arguing that radio sources are not at cosmological distances, they are nearby. Now we have basically no doubt that these sources are at cosmological distances. So this is out. Second interpretation, the interpretation of the cosmic microwave background radiation as relic radiation from the Big Bang. Also people were saying that CMB was not relic radiation from Big Bang. There were alternative models, like the steady state model and so on, in which CMB was not a relic radiation. But now I don't think we doubt that it is a relic radiation. And then there is third possibility. The standard FRW, it was not using Lemaitre, now we know that Lemaitre should be there, so FLRW universe model is not correct. So this is, we have to abandon it, basically. So he's saying that we have to abandon one of these three. We know that we cannot abandon one, not two. So we have to abandon the standard FLRW universe model, basically. So, oh, now I'm going to finish giving more time for discussions as you had asked me. So I'm going to finish with what Jim Peebles actually wrote in 2022, which goes back to what you were saying about the sociology. Why is it that we have got Hubble tension, which is also at 5 sigma, and there are hundreds and thousands of papers written? Why is it that the dipole tension, if I could call it anomalous dipole, which is, in my opinion, a lot more fundamental, has getting a tenth of that tension. And Jim Peebles has a very nice account of that, explanation of that, which I think I agree with. So he's saying the dipole anisotropy, hola, he's saying the dipole anisotropy in the distribution of objects at distances comparable to the Hubble length is about in the direction expected from the kinematic effect. So as we saw, the direction was very similar to the CMB dipole. If the dipole anisotropy in the CMB is due to our motion relative to the rest frame defined by the mean mass distribution. But the dipole amplitude is at least twice the prediction. This anomaly is about as well established as the Hubble tension. Yet the literature on the kinematic effect is much smaller than the 344 papers with the phrase Hubble tension. Now, this is 2022, 3 years ago, but now this is like more than 1,000, I think. In the abstract, in the NASA SAO, this is the astrophysical database of NASA, so astrophysics data system. I expect the difference is an inevitable consequence of the way we behave. I think it wraps it up quite well. What your first question is, why is it that people are not taking it more seriously? Because this is a fundamental challenge, and there it is. So I leave you with that, and we can maybe go to the discussion, have more
Yeah,
time for
great.
discussion.
Thank you so much, Roya, for an extraordinary lecture. I really mean that. Very clear, very enjoyable and exciting. And I think many of us are probably not so clear that the issue is so serious, precisely because, as you said, that's the way we behave. It's not being rubbed into us. So great. Uh, the talk is open for questions, please. So you can use the raise hand feature. And yeah, I could start with something naive, maybe, Roya. In grad school textbooks on cosmology, let's say long time ago, say 20, 30 years ago, we used to be told that, yeah, there is a CMB dipole anomaly, but we understand it is due to the motion of the Milky Way or the sun in the towards something. And it used to be presented as something well understood and not to be worried about. Do you agree with that? That's we were not worried about the CMB dipole the past. You see, it was. Is that correct?
Well, what is important is that let's say there's CMB dipole, and let's say it's correct. So I think what is important is that if the universe, if the metric is FLRW, if we have got lambda CDM, if this is the correct model of the universe, then this dipole has to be the same as the dipole given by distant sources. Basically, the CMB rest frame has to be the same as the rest frame of distant sources.
And in
And
20,
it's
30 years
not.
ago, we did not have this data to test this hypothesis.
Yeah, exactly. And this is very recent that we can test it now.
So,
And
the knife. Sorry, you finish.
and we are finding that they are not, the two rest frames are not the same, which, as
My
Elisa
knife.
Baldwin said, it means that the metric,
Mhm.
the universe doesn't follow our desire for simplicity, that, FLRW is great, and, we can write zillions of papers. Maybe the
The
nature
knife
doesn't.
question was that the motion of the sun around the center of the galaxy, that's well understood, is it? That's already subtracted out when we
Oh,
present
of
this.
course, yeah. So I don't have that transparency. Subi shows that in his talk. Is a transparency given by, it's a slide given by Joe Smooth. So there is the motion of the Earth around the sun. There is the motion of the sun around the galaxy. And then our galaxy and Andromeda, they form a local group.
Hmm.
So the barycenter of the local group has a motion. And when we talk really about CMB dipole, is the motion of that barycenter with respect to that uh, primordial fluctuation or the black body radiation. You can
Okay,
also
good.
consider the motion of the sun. So it's different. If you consider the motion of the sun, it's about 369 kilometers per second respect to the cosmic rest frame. And if you consider the motion of the barycenter of the local group is about 600, because there is the motion of the sun respect to the galaxy and then galaxy respect to the center of the local group. So there are all these different velocities that add up
Okay,
to that 600 kilometers per second.
okay, understood. Bernd, please go ahead.
Well, first of all, thank you for the great talk. Talk about a wonderful and long period of work. I have a question, also probably naive and related to how the community deals with findings it doesn't like, so to speak. Your findings are still, from a certain perspective, also still moderate or conservative compared to other stuff people have proposed. So you don't change anything about the laws of gravity. You just change a model for the cosmological model, and you use a model which is more general than the isotropic and homogeneous Friedman model. And by the way, the LPT model was developed to account for structure formation. So there was always the expectation that at some point we would see a deviation from the FRW model. Otherwise, there wouldn't be any galaxies or any structure we see. Well, I wouldn't be here to talk about this if there has been no structure formation. So I don't understand why there's such a resistance. Okay, the model becomes more complicated if you have different scaling factors. I see that, but maybe this could also explain a lot of other anomalies we see without having to invoke exotic physics. You just have to, relatively speaking, conservatively adapt your model, but don't have to change your gravity theory of gravity or add new ingredients like dark energy or dark matter, which was done to explain other stuff where the community was quite easy and eagerly doing this. And now you're just, sorry for framing it this way, but this is still quite conservative compared to what people have done before, what has been proposed to solve some of the tensions we have seen. So this is something which I find a little strange.
Well, we are moving towards, we are becoming more and more conservative in all aspects. So I'm not surprised. But yeah, you're absolutely right. I mean, we are just looking at data and we are saying, well, this data doesn't agree. So yeah, they don't. Yeah, I mean, this standard model of cosmology is a phenomenological model, as I showed you, and it fits data. It's based on two unknowns, lambda and CDM. I mean, we haven't detected dark matter and dark energy, as you've seen, as you know very well, because most of you are theoretical physicists, is the biggest challenge of physics today. And this is the foundation of this model. So, yeah.
Okay. Okay, this would be a follow-up question, but I've seen from papers on structure formation, for example, there's Thomas Buchert in Lyon, who said that you can also explain dark energy and some aspects of dark matter also by going to inhomogeneous cosmological models. So could this also explain some of the things we normally attribute to at least dark energy?
So I think what Thomas, if Subi knows best because he worked on this and he knows this. So I think what Thomas Buchert is saying is different. So he's actually not talking about inhomogeneous metric like Sekeres model and so on. What he's saying is that the structure formation leads to inhomogeneity. This inhomogeneity will affect the backgrounds.
Yes,
and could act as lambda.
Yeah, okay.
That's what he's saying, yes.
Okay. but could it be a possibility also if you look? It seems to be that we have some inhomogeneities, and then we should also get some back reaction from this. So
Yes. So I'm not sure. I don't know whether Thomas Bouquet has done anything after we have found this cosmic dipole anomaly.
I will inform him. I meet him sometimes when he's in Munich, so I will forward this information to him.
Yeah. Yes.
Okay, thank you very much.
Thank you. Thank you. Veselin, please go ahead. Please unmute yourself.
Thank you very much. It was very exciting and very enlightening talk. And I agree with Njandar that it's the way we think and behave that we kind of don't pay attention. We know there's a dipole problem and tension, but we haven't paid attention to look into it like you presented to us and say, wow, that's serious. And I have a question. Basically, there are three systems that I see here. I mean, one is us as observers. One is the CMB during recombination, which is far in the past. And there is the local distribution of matter, which is up to some Z. So what if we interpret this like first the dipole with respect to CMB is our motion with respect to CMB. Now you're showing that the dipole with respect to the local matter is different from the CMB. Can we interpret this as a motion of the local matter with respect to the CMB?
Yes. Yes. So you can, but this local matter, exactly as you said, so we can talk about our motion with respect to CMB or the motion of local matter with respect to CMB, but what is expected if the universe follows FLRW or is lambda CDM is that this motion of local matter with respect to CMB has to die away when you go to larger and larger distances. This motion of local matter is called bulk flow, and if the universe is isotropic and homogeneous on larger scale, this has to go to zero. And what I showed you in the book on supernovae is that this doesn't go zero. So it's the two different ways of looking at it. You can either look at our motion with respect to the local distribution, or you can look at the motion of the local bulk of matter with respect to the CMB. So our motion with respect to the distribution on larger and larger scale has to be the same as our motion with respect to CMB. Now, if you look at the local motion of the local matter, then this motion has to go to zero because the matter frame, as you go to larger and larger scale, has to be the same as radiation frame in lambda CDM. And so both way you look at it, there is anomaly. This is the same anomaly, but looking at it from two different windows, if you like.
Yeah, I understand. Thanks for that. So, but still, that they are very different Z's. I mean, the CMB is coming from about 1,000 Z, when the local one is within 1, 2, 3, or 4 the 1 Z.
Yes, but yes. So when you look at quasars, they are at redshift of 1 and above, basically, right? So when you look at local ones, Virgo is very near. Shapley is at about 150 megaparsec. So, you're almost approaching 0.1, where you would, in lambda CDM, you would expect there to be no motion with respect to the, you see. So we have to compare with the model. Lambda CDM says that when you look at scales of Shapley, which is Z equal more or less 0.07, 0.1, then I don't expect any motion with respect to CMB. I have reached the rest frame of the CMB. And that is what is not reached. It is very different, but this is the prediction of the model, of the standard model of cosmology.
Yeah, thank you.
Thank you.
Yeah, I think I should read out a related comment in the chat because it's very connected to what you said. Andrew is commenting, it is strange that the directions agree but the velocities don't. If there were a genuine difference, would it not be in some random direction, not necessarily the CMB direction? And then Subir's reply, Andrew, what if our peculiar velocity, which gives rise to the CMB dipole, were to continue much further than expected in lambda CDM? where it should decay away in 100 megaparsec. After all, we already see it extending beyond 300 megaparsec. This would be very weird, of course, but that would explain the alignment. I don't quite get the gist. Maybe you could please explain this to us. Yeah.
Yes. So yes. So and yeah, I agree with Andrew, but I wouldn't use the same term that is strange. I would say this gives us a big clue as what is the origin. You see, so that the directions are more or less the same, and the amplitudes are different. So because we have to find out now what is causing it, what is the alternative theory, and this is a good clue that the directions are similar. Yeah, it is strange, but it's a big clue to go forward. And what
So,
I think Subir is saying, but Subir can talk because he can explain it himself. He's there. Is that what if this local anisotropic distribution of matter, which is more or less the same direction of CMB and is responsible for a big part of our motion with respect to CMB, just continues further away. And if that is the case, then lambda CDM cannot hold because we expect that not to be. We expect that above a scale of 200, 300 megaparsec, you should have no direction. Basically, the universe is isotropic.
so what you and Subir are saying is that the alignment can be understood as saying that the bulk velocities should have decayed but are not decaying.
Not the alignments would not say that. The bulk, so this is what we observe. The bulk flow should have decayed, but it's not decaying. The bulk flow is in the same direction as CMB because the same objects that are pulling us and explain good part of CMB dipole are those objects that are also pulling the other galaxies. So that is why the bulk motion is aligned more or less with the direction of CMB. So that we understand. But why is it that the rest frame of quasars and CMB are sort of at 20 degree, whereas they have a completely different, correspond to completely different dipole. One is twice the other.
Yes.
That we don't know. But
Thank
Subir
you.
maybe can elaborate.
Subir, please come in. I think you can add to the discussion. Subir?
First, can I just say this remark by Vance a little while ago as to why are people resisting dropping FLRW? Because after all, we should have expected at some point you would need to, once you see that the universe is inhomogeneous in its structure. The reason is simply that, of course, we all know the universe is inhomogeneous. It's not exactly FLRW, but the conclusion that it is dominated by a cosmological constant or evolving dark energy, as is the case today, rests entirely on the assumption of FLRW. And this is not as appreciated as it should be. So you would have heard about the recent results from the DAISY experiment, dark energy spectroscopic instrument. They have beautiful data covering a third of the sky, millions of redshifts, but they still assume FLRW in order to conclude that there is dark energy, because what they actually measure on the sky, which is baryon acoustic oscillations, is not a direct measure of dark energy. It's a measure of the matter density or the Hubble expansion rate. So everything is interpreted in terms of a model, and that model crucially assumes FLRW. This is the point. Secondly, so that would explain why people are reluctant to give up FLRW, because if that goes, then along with that goes the entire empire of dark energy, lambda CDM, which is of course something that the community is in the main engaged with. So, okay, that's just a remark. And quickly to return to Andrew Hamilton's point, yes, it is very puzzling that the directions is agree but the amplitudes don't, because that would then suggest that it is the same underlying reason, and for some reason it is quantitatively a different number for the matter than for the CMP. And one possible way to do that would be to invoke some sort of a super horizon perturbation. In fact, this has been discussed some time ago. Roya didn't have time to touch on this, but this was suggested by Mike Gunn and worked on by Turner and others. Unfortunately, on closer examination, it turns out that such a super horizon perturbation, which would have to be isocurvature, it can affect the CMB, but it doesn't actually have commensurate effect on the matter. So, in order to, I mean, you could argue that our real velocity is what is being indicated by the matter, so around 600 something kilometers per second. And the reason why it is only half of that for the CMB is because this perturbation is cancelling it. It can be a negative contribution. But then Andrew's point stands, why are they in the same direction? That would then have to be an accident. So, it's not a very persuasive thing. But the other alternative, which is what I suggested in the chat box, that our local peculiar velocity is extending out to where these quasars are, that too is ridiculous because these quasars are at thousands of megaparsecs, right? If you had a bulk flow extending out thousands of megaparsecs, first of all, to create such a flow would require an amount of matter which is of order the entire amount of matter in the universe because of the 1 by r square law, right? To create a flow as fast as even the observed thing that we see, which is 300 kilometers per second, up to 300 megaparsecs, that already requires a mass of order a supercluster mass. And we don't see it on the sky. Nobody has seen the great attractor. So there are a lot of puzzles here. And the way forward is to make more observations to measure this anomalous dipole in different redshift slices. And that data is coming very soon. There is a satellite just launched earlier this year in April called SphereX, which is scanning the entire sky, and it will have its first full sky map in 6 months, and that will be able to if check if what we are saying is true, and B, because it has 100 photometric bands, it can measure redshifts to 1% accuracy, and it can allow us to do tomography in redshifts. And then there is Euclid, which has already got data, release it soon. And soon there will also be Rubin and LSST. And in the longer run, the square kilometer array, etc. So there's plenty of data coming. We just have to be patient and wait for the data because this is not a simple problem. Now, and the last remark is with regard to what was said about Thomas Buchert's work. So Thomas Buchert made the point that if you had a perturbed universe, then when you do smoothing in order to get a effective FLRW metric, in that smoothing scheme, there is a term which comes out of smoothing over some patch of size, some scale. That term looks like a cosmological constant, and therefore it can look like apparent acceleration. But as Thomas recognized himself, the smoothing is being done on constant time-like surfaces. What you really need to do is to take into account the effect of inhomogeneities along our past light cone, because that's where you make the observations. You do not make observations on a constant time surface. And unfortunately, in GR, these two things don't commute, right? So that is why it is very hard to do an analytic calculation of this back reaction that Thomas identified, although it has all the required properties. But quantitatively, all you can say is that it is proportional to the variance of the fluctuations. And then there is an argument as to how much this variance is. You could say that the fluctuations are only 10 to the minus 5 on the last scattering surface. So the variance is 10 to the minus 10, i.e. negligible. But then I could say, well, the fluctuations are of order 1 today, and the square of 1 is also 1. So the answer is something between 10 to the minus 10 and 1. And to cut short a long debate, this is basically the state of the problem. The only way forward, as Martin Rees actually remarked to me some years ago, and this is now happening, is if people do general relativistic simulations of large-scale structure formation and then construct light cones in their simulation and look at the effects on observables like luminosity distance, etc., to see what the effects of back reaction are. And the first such simulations are being done, but obviously they're very hard to do. They are not anywhere near as big as the ones that have been done with Newtonian physics. Those are the ones that give you all those beautiful color plots and cartoons and movies, but they are not realistic. They don't take into account the subtle effects you're talking about. So I'm afraid again we have to be patient and wait for these guys to get their simulations up to speed so that we can get a clear answer as to the effect of back reaction. Right? Sorry, Roya, for such a long answer, but
Thank
you'd
you.
want me to
Thank you.
comment
Yeah.
on this.
Sure. Thank
Yeah,
you.
thank you, thank you. Could
Can
you
I
please,
respond?
Yeah,
Can
please.
I?
yeah,
Since,
please
since
go
I
ahead. Please go ahead. Please go ahead.
since I provoked some of this discussion,
Hmm.
and I agree with a lot of what you say, Sabir, that yes, future observations are going to be crucial in deciding these things. But the lambda CDM model has been so successful over the last few decades that one has grown a large Bayesian prior against one observation, or you would say, well, there's two sets of tensions going on here, and maybe there's some other ones as well. But it's usually these things have a tendency to find themselves caused by some astrophysical, some systematic in the astrophysics, and I wonder, maybe so for some reason you're misestimating the spectra of the distant quasars or something. I'm just guessing. I agree with Roya that it's a clue. It's still strange. I'm trying to think what theoretical thing could possibly make this thing happen. And Subir, I'm not entirely convinced. I'll have to go offline and think about large-scale motion of the dark matter dating from before recombination versus the radiation. I mean, that's not entirely implausible, it seems to me, but I'd like to think about how plausible that might be. Regarding the DESI announcement earlier this year, they find a result which is close to they're looking for the equation of state, and they get some result for the W, which is just slightly different from -1. It's about, I forget exactly how many sigma, it's sort of 1 sigma away. And so you can say, well, that's an astounding success for a model in which it's lambda and not something else. And the departure away from -1 is in the direction of a decaying lambda, which makes some sense. We don't actually know whether the cosmological constant to today, the dark energy, we don't know whether it's stable or not. All previous cosmological constants, if you will, arising from the Higgs fields, like grand unification, they were all unstable and decayed, and we don't know definitely whether the dark energy today
They are also
is stable.
60 orders of magnitude bigger. So this cosmological constant that is being inferred from the data has got nothing to do with quantum field theory or particle physics. This has
Oh,
been
you don't know
recognized.
that? Oh,
We
that's
do know
just an
that
assertion.
because, well, there's only this small factor of 10 to the 60 to explain them. But anyway,
120, 10 to the 120.
10 to the 120 if you like, depends. But let me address two questions very quickly, Andrew. One is that you're absolutely right. It could be a systematic effect. To that extent, that paper that I referred to, which we have just put out on archive yesterday, that addresses all the concerns that have been raised. So please, we would appreciate it if you and others take a look at it and try to find something wrong in what we have done. We would love that, right? Secondly, the point that you made about DAISY, since you appreciate cosmological data, let me ask you just one question. DAISY has 6 million redshifts over a third of the sky, okay, from which they infer baryon acoustic oscillations. It comes out at the right scale for lambda CDM universe, and as you say, they infer something very close to lambda. Can I just ask one question, which you may put forward to your DAISY colleagues? Have they actually checked that their signal is the same in every direction in the sky they look at?
I don't have any inside information on
I know
that.
the answer to this. They haven't, because this assumption of that the universe is isotropic is so deeply embedded in our brains that even when we have the data, we are not bothering to do the first check that you should do to test if that assumption is correct. Okay. Now, I'm not in the DAISY collaboration. It is possible that there is some, practical reason why they haven't done that. But I find it astounding that even when they've got such amazing data, that the first thing they don't do is a check of the assumption that they make to draw the inferences that they do, which are very profound for fundamental physics. The idea of evolving dark energy and so on is, making all my string theory colleagues sort of tie themselves into knots. Okay. And the whole thing rests on this assumption of isotropy. So you would imagine that a good observer, regardless of the question of whether that lambda is natural or unnatural, anything like that, the first thing you do is to check that your BAO signal is actually the same over the third of the sky that you have looked at. Why haven't they done that? So if you can answer that question, then but let me stop here.
So
I'm
Roya wants
dominating
to say something. Roya, go ahead.
I want to ask Andre a question.
you. That's right. Get back at him.
So Andrew, you said it could be systematics, and this is quite worrying because I've heard that for the last 15 years. It was systematic, and then I say, what's systematic? It's not clear. So for me, it's very frustrating. Now, first, I want to emphasize that there are two data sets completely independent, completely different systematic to are showing the same thing. And second is my question, would you say the Hubble tension is a systematic?
I'm not going to make a decision here. Look, I'll follow the Subir rule, which is wait till the observations converge. What we've got is two different teams getting two different results. Both of them are believable, but why is I like to put a theoretical understanding behind these things. It's lovely when the experimentalists come up with, or the observers come up with tensions, but making sense of them is another thing. And so I don't know, but source crowding, spectra, you name it. I haven't thought about these things. You've thought about this.
To be
much
fair,
more.
You don't have any understanding of lambda either.
I want to.
Well, let me push back Andrew, on this. It is quite clear. It's quite clear that right now the quantum field theory people and the string theory people, those who worry about what happens at high energy, have no understanding whatsoever of what lambda is, because their prediction is 100 or more orders of magnitude out. So I don't believe what they say.
Yeah, so I think, to continue with what you said, I think lambda CDM is partly also about the way we behave. Lambda has already been discussed, its difficulties. I think the same goes for dark matter. Where is the dark matter? Where is the dark matter candidate? And then when you come to galactic scales, then you see the rotation curve that telling you that there's a critical acceleration beyond which the curve becomes flat. And then as far as we know, the observations of the curve continues to be flat. But if it was dark matter, it should become Keplerian when you go far out. Then similarly, the baryonic Tully-Fisher relation, as far as I know, there's no great explanation for this with dark matter. So I think there are great issues in our understanding of dark matter, apart from the fact that we have not detected it experimentally. That can wait. Yeah, so anyway, I will stop. I think Roger has a question. Subir, Roger, please go ahead.
Okay. Can you hear me?
Yes.
Okay. No, so I'm sorry I missed a lot of the early part of your talk, but I wondered whether you had a comment to make about the recent observations of Alexia Lopez of the Great Arc and Large Ring, which do seem to go against current cosmological picture.
Yes, of course. And actually, we organized a conference in Royal Society last year with Subir, and she was one of the speakers. So yeah, that's they are finding a huge arc, and it's not clear. So people are saying again it's systematics, and they are not taking I don't know, doing the observations properly, but they insist that it's correct. Subir, you have probably more to say. I have not really looked that into detail.
No, I agree with what you said. I think as Roger knows, there was a counter statement made by people who do simulations of structure formation that the arc might arise in a simulation, That is also debatable because they have kind of questioned that whether they're really talking about the same thing. But they also see this ring, and that certainly is far more perplexing. And there is, although people have looked for rings, in fact, due to baryon acoustic oscillation, Brent Tully was one that did that. The scale of that, as Roger knows, is very different. So I think what Lopez and collaborators have found is very intriguing. And again, I think it's a matter of scale. So, earlier when we were talking with Andrew, we are talking about several hundred people who are focused on doing lambda CDM, maybe thousands, against maybe a dozen of us who are looking at this problem here. And similarly, Alexia is just finished her PhD. There are maybe a handful of people who are doing that kind of work, as opposed to the armies that are amassed against them. So it's not a very balanced situation. And that's really because I think a lot of people who have the tools, both technical and intellectual, to address these issues. Well, okay, we are among friends here, so I'll say this candidly. I find that young people are genuinely afraid of working on these things because they are concerned that it will affect their future, their careers. And I find this extremely depressing, to say the least. I mean, people like Andrew and I can talk about this and joke about it, and we all know exactly where we stand, which is as it should be, because after all, we are doing science because it interests us. We are not in the business of selling used cars. But I'm afraid a lot of young people, I find, actually are genuinely concerned that if they work on something like this, which is not mainstream, not bandwagon, that they won't get their next postdoc, they won't get a job. They'll be thought of as cranks. And this, sorry, I didn't mean to go on. I do find it extremely depressing. Sorry, I'll stop here.
Thank you. So I'll come back to some other questions. Roger, you have something more to add?
About this? Well, you see, the scheme that I favor is the conformal cyclic cosmology model, which would agree with many of the things that one sees, but the arc and ring that seems to be there, according to Alexia Lopez's observations, would be a prediction of the theory. Nobody actually made this prediction, but after seeing her results, I would say it is a prediction of this theory. It would indicate that there were, in the previous eon, that is to say prior to the Big Bang, there would have been collisions between supermassive black holes, and these would produce great gravitational wave signals, which could trigger the creation of galaxies in the early stages where galaxy formation takes place. And you would expect to see rings and things like this sort, something that nobody thought of before Alexia had made these claims. So the argument I would make is that there are lots of these things all over the sky, and people should look for them.
Well, that's the point, Roger. Nobody is looking for them for the reason I gave. And the ring, you're right. It is not something that has appeared in any simulations done to date. The arc, one could imagine, could emerge in some way. That's
but she thinks the arc is probably a ring.
Yeah, well, the Durham group have claimed that they see such things in their latest simulations, but Alexia and co have fought back against that with good reason, I think. But certainly the ring is much more compelling an anomaly.
By the way, regarding the career question for junior scientists, what you have to tell them is to study a bit of game theory. If you go into these fringe things, you get a much higher likelihood for a binary outcome. So either, the thing is, if you do mainstream, you have a chance for a job everywhere of like 10%. If you do some fringe things, either people love it or hate it. So, but at the end of the day, you only need to get a job at one place. So,
well, I hear what you're saying. I'm just reporting what I find is the case. amongst the
Okay.
the people that I
Yeah,
have
so maybe
dealt with.
let's get back to
Yeah.
yeah, so there are quite a few more comments. I will come back to them. But I think we have a new question. Sergey, would you please go ahead?
Yes. Can you hear me?
Yes, yes. Go
Yeah,
ahead,
yeah.
please.
Okay. So first of all, Roya, thank you for the wonderful talk. It was very insightful. I actually rushed back all the way from work to hear it. But let me also just quickly say, Subir, that let me alleviate your depression a little bit because I am an undergraduate student and I'm very interested in these, let's say,
Welcome,
non-standard approaches. So
welcome.
one thing that I wanted to ask perhaps the entire round here is that about the sort of initial conditions. So Roya, if I may ask you, could you go forward a few slides? I'll just say stop. So if you could, you did have a slide.
Forward or?
Forward, yes, forward.
No, let me just put, oh.
Yeah, stop. One more back. Right. So essentially, you concluded here that there's sort of, so from the work that you have done and the observations that you've interpreted, there's these three things that you can sort of, one of them you can discard. And you argued that the first two are sort of, you wouldn't discard, but that you would go to the standard FRW universe models and sort of reevaluate that. Now, there has been a recent paper. It's come out like a few weeks ago, so I don't know if you have seen that, but it has to do essentially with the CMB and with the sort of earliest observed massive galaxies in the universe. So I remember a recent talk here was by Stacy McGough, where he showed that the formation of so galaxies are too massive too early. And one different observation that points to this also is the fact that like elliptical galaxies appear to be some of the most ancient objects in the universe. And so this paper I'm talking about, so the title is The Impact of Early Massive Galaxy Formation on the Cosmic Microwave Background. Essentially, they argue that, the authors, that if you have these elliptical galaxies that form very early, right? So they form in this monolithic collapse, have an enormous starburst, right? And you essentially calculate how many of them there are sort of across the sky at these cosmological distances, then it comes out in their most conservative estimate that the radiation that is produced by this initial starburst comes out as around 1.4% of the energy in the CMB, right? And so if you think about the implication of this now, that the temperature fluctuations in the CMB are on the order of 10 to the minus 5 Kelvin, and then the energy deposited by these sort of enormous energy sources, right, is 1.4%. So that is way out of the range of the temperature fluctuations of, temperature fluctuations of the CMB. So is it then sort of not possible that the interpretation of the CMB as we understand it, or as we think we understand it in the standard paradigm, that is the, let's say, initial conditions that are also always used for the large-scale simulations, that those may not be valid?
Well, so I think I know this. So with the JWST also, they're observing galaxies and sources at very high redshift that are not expected to be there in lambda CDM and in the galaxy formation scenario in lambda CDM. So that is already a problem. And so in lambda CDM, actually, elliptical galaxies usually form from the merger of spiral galaxies. And so observing too many elliptical galaxies as high redshift is inverse to the hierarchical formation of a galaxy. So that's a problem. But you can always say, okay, there are odd elliptical galaxies at very high redshift. It's really a question of number, how many there are. But that galaxy, but the light coming from these elliptical galaxies, even if there are very many, would be actually the source of CMB radiation. I don't think so, really.
Well, if I may clarify, it may not be, don't think of it as the source of the CMB radiation, but rather as a contaminant, right? Which you have to take into account, because really, when the power spectrum, what is it derived from? You have to clean up data, and quite extensively, before anything comes out, right? So there's assumptions going into that, right?
Yeah, of course, yeah. So there's the foreground. They would add to the foreground contamination. But then, so CMB photons would, on their way, so some people have actually argued that they could sort of cause the first formation of first stars. And then, of course, in the clusters, there would be thermal and kinetic effect. So thermal and Tourniaev-Zeldovich, kinetic Tourniaev-Zeldovich effect on the CMB photons. And of course, if there are elliptical galaxies at very high redshift, then they should also, I think, have an effect. Yeah, because elliptical galaxies are very massive. So
Well,
yeah,
just the point, perhaps the question is a bit unfair to you, because it's not like a very specific question, but perhaps it is more a point to raise that you seem to have very quickly discarded point B, when there may be a possibility that the initial conditions, as we think that we understand them, may just be different, and then the entire assumption of the cosmological principle, right? If you have to evaluate it on those scales, what does that mean going forward? And all I am asking myself then is, well, what does it mean? I have no idea, so I was curious just to hear.
Yes, the second thing I think that Ellis and Baldwin are referring to is that if the CMB radiation is not a black body radiation, then the calculation that was done by Wilkinson and Peebles would not be correct, right? So because they assume the CMB is a black body radiation, and then they calculated, okay, what is the velocity of the observer that would give this dipole anisotropy? And so if it wasn't the black body radiation, then that calculation is not valid.
But the black body we know from Kobe is an observational statement. Now, you could question whether that is indeed true, but almost, well, I think it's generally accepted that Kobe measured the radiation spectrum by comparison with an internal black body, and they claim it is so good that any energy release is restricted to be less than 10 to the minus 4, right? So by the time you're talking about these galaxies, we've been discussing this with other people, it is too late, for the universe is no longer ionized, so you can't directly put a Bose-Einstein type of distortion. But as Roya just mentioned, you'd get a Y-type distortion. That's the Tourniaev-Zeldovich kind of effect. And as it happens, Kobe claims that Y-type distortions are less than 10 to the minus 4, and the energy release commensurately has to be less than that. So I have no idea how these two statements can be reconciled. You have a direct confrontation. You are absolutely right that there is something is got to give here. So on the one hand, we have the most, perhaps the only precision measurement ever made in cosmology, which is the spectrum of the CMB by Kobe, which was, as you know, Nobel Prize was awarded for the interferometer measurement that made that possible. And so the only other way this radiation released from these early objects would evidence itself would be in the way of foregrounds, as Roya also mentioned. And indeed, when we determine the CMB, what people do, like Planck and WMAP and so on, is that for every pixel in the sky they look at, they match it by a combination of a synchrotron spectrum from galactic radio emission, which is a falling spectrum, a dust emission from the galaxy, which is a rising spectrum, and the CMB spectrum, which is in the middle, which is flat over that frequency range, which is around 100, 200 gigahertz. Now, this spectrum of these early galaxies that you're talking about is presumably very different, right? So I think the quantitative question now would be to ask if this so-called internal linear combination method, which is called SMICA in Planck, whether that already takes into account contamination of this kind, because the authors of Planck say that their maps are good to better than 1 microkelvin. The CMB fluctuations are of order 60 microkelvin or 80 microkelvin at the peak. They claim to have got it right to almost 1%, right? Whereas what you're talking about, as you just said, is something like a few percent energy release of the CMP. In fact, some are even arguing that the this might actually account for all of the CMP. But we have been here before. In the steady state theory, the CMB was meant to be thermalized starlight, which also has the same energy density as the CMB. And Fred Hoyle invented graphite whiskers, which would actually absorb starlight and re-radiate it in microwaves and give you a CMB like spectrum, which was a good idea. Unfortunately, it doesn't give the kind of black body that Kobe observed. It gives you something close to a black body, but not good enough. To make that good enough, you would need to have so many of these graphite whiskers surrounding us that they would entirely blot out our view of the extragalactic universe. Right? So the same kind of argument, I think, would apply in this case. But I take your point that there is a observation by JWST of these objects. So I think this deserves more thought, and but the crucial thing is the CMB spectrum.
Yeah, yeah. So to continue on this FLRW issue, Roya, could I ask you, are we in agreement that the very early universe was FLRW as confirmed by Big Bang nucleosynthesis, and it predicted a relic CMB, which we see? So is that part correct? And can we say then that when structure formation begins and goes nonlinear, something goes very wrong, perhaps with the assumption of a present universe being on the average FLRW?
Well, I would hesitate actually to say that anything from Big Bang would predict a metric FLRW. So there's so you can get the CMB spectrum that is very, very close to Gaussian, but it doesn't say anything about the metric. I mean, you don't have to have FLRW. There's nothing there to.
No, but I could say that it predicts Big Bang nucleosynthesis abundances of light elements correctly. That required a metric, isn't it?
So CMB itself is temperature fluctuation is very homogeneous and isotropic. So this is radiation. So yes, and then we know that the radiation is related to the fluctuation in the density field, and yes, if you can take the fluctuations in the CMB, the homogeneity and isotropy of that, then yeah, early universe, very early. It could be FLRW could be a background metric in that sense.
Thank you.
So
we could agree with that.
I wanted to add, we just had a workshop on Big Bang nucleosynthesis held at CERN, and the question was raised as to whether we have any evidence that the primordial abundance of helium is actually the same in every direction. That would be part of the FLRW. And the answer is we have no idea, because we only observe it in about 100 local galaxies. Deuterium we observe along only a few directions at redshift around 1 or 2. So actually, apart from the argument that Roya just gave, that the CMB looks pretty isotropic after you subtract out this dipole anisotropy, BBN, there is general agreement of what we calculate in the FLRW framework, right? That is one strong evidence for FLRW at that stage. But we actually observationally, if you are going to be a hardcore observational astronomer and ask, are the abundances of the primordial elements the same in every place in the universe? Answer is we just don't have the data for that. And secondly, the theoretical point, which might be more persuasive, is if there was any anisotropy at the BBN epoch or the CMB epoch, we know that all anisotropy, shear, vorticity, all that stuff, it decays extremely rapidly with the scale factor, right? As 8 to the 5, 6, 4, much, much more steeply than matter or radiation or anything. So it would be extremely unlikely if this anisotropy that we are seeing today is a relic of the early universe. I think what you said is more likely. It could be something to do with cosmic structure. And recall that all the evidence for cosmological constant is also associated with the formation of cosmic structure around redshift around of order unity. And there is some interesting recent work which I've pasted in the chat by Tim Clifton and his student Theodore Anton from Queen Mary, who have in fact pursued that idea that as to whether one can get anisotropy emerging at the time of structure formation.
Thank you. Thank you. Yeah.
So if this is turns out to be true, then the early universe is still FLRW. The discussions of the early universe remain the same. However, the late universe is not FLRW, and therefore the deduction of lambda has to be thrown out. That's and that is sufficiently important in my view that if that would be worth it.
Yeah, thank you. Thank you. Bernd, I'll just get back to you. I want to read out the comments, which I didn't do so far. So Stacy has left, but he left this important comment. He says, I will add that I was very skeptical of claims of deviations from the cosmological principle just a couple of years ago. Your work and the work of your collaborators has gone a long way to convince me that it is a serious issue. So I think that's a nice comment from Stacy.
He gets his £5, yes.
And Claudio said something about the cosmological constant. When you consider modified measure theories, you can get rid of the cosmological constant problem. When there is some discussion on that, please, you can see the chat for that. And I think there were some more references given after that. Subir left a reference, I think.
Yeah, that's just a review by Norman Huyes, who classified all the suggested solutions to the cosmological constant problem, none of which work in that thing. So I would suggest looking at that first.
Okay. Then Igor Kanachikov also left. He gave a talk some time back in our series. So his comment is, let me recall that in our recent EPL paper, there's a reference. And in his recent OSMU talk here, the value of the cosmological constant is estimated to be close to the observable value within several orders of magnitude of error, where the inverse spatial volume is on the order of hadronic scale of the mass gap in the Young-Mills sector of the standard model. So if you are interested, please see the recording of Igor's talk. Claudia, did you want to say something more about lambda?
Not really. I mean, this is still in development, but I mean, when you have modified measures, then so if the measure is an independent degree of freedom, then simply the cosmological constant becomes a constant of integration. So yeah, and currently the one thing is looking at it basically as an infrared regulator, an infrared cutoff that restricts the size of the interacting region.
That is one of the categories Norman Weiss talks about. One category is where you think it is a Lagrange multiplier. Another category is where you think it's a constant of integration, and so on, so on. So have a look.
I'll have a look. Will be interesting to see.
I just mentioned that because I thought it was actually this guy's PhD thesis. So his supervisor, Gerard Touft, who of course didn't solve the cosmological constant problem, and he couldn't. He set his student the task of looking at every proposed solution and classifying it as to what category of solution it came in. The point being that lambda is of order the Hubble parameter squared, today's Hubble parameter, H naught, which is the infrared scale you're talking about. So in the absence of a UV-IR connection in any local quantum field theory that we are aware of, that is, as you know, a pretty serious problem. But it is worth thinking about, yes.
I mean, at the end of the day, the only thing that matters, the only real scale we have is the ratio between the Planck length and the scale of the cosmological horizon. That is the thing that needs explanation.
Those are the only two fundamental scales in the universe, I agree.
Yeah.
The difference being that the Planck scale does not change with time, whereas the cosmological horizon does change with time, because that's just 1 over the expansion rate. So today...
Yeah, but the cosmological constant shouldn't change with time, so this would be...
Correct. So that is my point. That is precisely my point, that when you infer it from the data, that this is something that people don't appreciate. Lambda is 2 times h sub 0 square. H sub 0 is the present day Hubble parameter, which in energy units is 10 to the minus 42 GeV. It is an infrared scale. It is the size of the universe, and it is changing with time. So it cannot have anything to do with the fundamental quantity. It is neither fundamental nor constant.
I mean, it can. There could be so that it's calculated via the present day Hubble constant doesn't tell you that there isn't a underlying actual constant that has nothing to do with the expansion of the horizon. I mean, if you have.
I'm sorry, you might have misunderstood. That is how it comes out from the observations. When you deduce it from the data, the only scale in the data is h sub 0. That enters into every cosmological observation. That's all. Okay, so lambda is naturally of order h sub 0 square. It is in fact numerically 2 times h sub 0 square, right? And I'm saying that is why our suspicion is more on the fact that it is dictated to be something of that order in any model based on FLRW, which assumes isotropy, because that leads to a sum rule: omega matter plus omega lambda plus omega curvature equals 1. That is the short statement of the FLRW metric, right? And so you don't measure omega lambda directly, you measure omega matter, you measure omega curvature, and they don't add up to 1, they add up to 0.3. So you conclude that omega lambda is 1 minus 0.3 equals 0.7. And since omega lambda is lambda over 3 times h naught square, that means lambda is 2 times h naught square. But what I'm suggesting is that this scale is forced upon lambda because of the rigid framework of the model in which you're interpreting the data. There is no other scale in the problem. Okay, and so before we start constructing models for lambda, theoretical models, I think one should pay attention to how do you know that it is there. We don't actually.
In my view, the best theory would be where theoretically also the cosmological constant is 0. In observations also it is 0, and what is pretending to be lambda is something different.
I actually have absolutely no issue with the positive cosmological constant. It guarantees if you have a positive lambda and a non-zero Planck length, what this tells you is that you have an overall finite number of degrees of freedom in the universe. This is completely fine. I mean, it's a really huge number of degrees of freedom, but this is basically the lesson you can draw from that.
Mm-hmm. Yes.
Okay, let's go ahead. Sorry, Bern, to keep you wait so long. Please go ahead.
Everything is fine. So I had my question, so this is a bonus. I would have a question, provided that future data show that we have this bulk flow also over very large distances. Would this point to modified gravity? Because you said there wouldn't just be not enough matter to cause this bulk flow if you use the gravity laws we have at the moment. So provided that future data, and here I'm a little bit impatient, I have to admit, and provided it's not a systematic, let's just these two assumptions we have to take for my question. Would this provide a hint towards modified gravity so that gravity is stronger than we expect?
Yeah, it could. And so some people actually, because already the bulk flow is larger than even now, with the data, is larger than is expected. So some people have tried to use modified gravity models like extra dimensions models to, for example, extra dimension models, FR models, to explain this bulk flow. But of course, you know, you need more data.
Yes,
The-
yes,
the-
And I think I agree with Andrew. And these models have to satisfy a whole bunch of data, right? So there is a bulk flow data, there is our quasar, anomalous cosmic dipole problem, and then, you know, there are other data, right? So
yeah. Might it be useful to study structure formation with a relativistic version of Milgrom's Mond? Do we expect some surprises there?
have people, so they have not done, have they not done that? I think they have done that. So Benoit Famé, I think, has been doing these simulations with Milgrom. So Milgrom's modified Newtonian dynamics
I think the
explains very well the
difficulty at
rotation curve, but it
yeah,
has
the
a problem
difficulty,
at cluster scales, right? I mean, at cluster scales, you need to.
yeah, they suggest there are ways out, like missing baryons
Nice,
is
okay.
one possibility. And
Yes.
Stacy is not too happy with it, but Milgram is okay with missing baryons. I
Yeah.
was saying that on the cosmological scale, the difficulty they face is, suppose you want to do cosmology with Einstein equations and Mond, because the background curvature is being given by Einstein equations. How do I add Mond to that? I mean, do I add it as a source term on the right hand side of Einstein equations? It's not clear.
So
If
these
you
are
could,
low, yeah. So this is, I mean, it's more or less like Newton's gravity, which is a low or weak gravity limit of Einstein general relativity. So
yes,
as long as Moon doesn't have problem in solar system, which I don't think it has,
yeah,
then it is a viable limit of GR. But there is not a GR, right? So there is this
and
Teves
modified
model.
GR, modified
Well, it's a
GR.
Teves model of Bekenstein.
Yeah, yeah. For
So
example,
that's the Lagrangian that you write for Mond,
yeah.
which is not really GR. And some people have tried to fit CMB observations with that. I think they had problem with third peak, right?
Yeah, yeah, yeah.
Yeah.
So
There's also a model, a relativistic version, this ether scalar tensor model
yeah,
from
yeah.
the group in the Czech Republic. I forgot his
Yeah.
name.
So
They,
yes,
they
that's
fit.
right.
Cordis,
Konstantinos Cordis.
Yeah.
Cordis,
Thank you.
yeah,
Yes,
yeah.
yes.
He is
Thank
actually visiting us right now here.
Okay.
So what they have shown is that you can always write down a model which will give you the CMB as exactly as it is. However, that model need not always be as nice as one would like it to be. In
yeah,
fact, it may have negative kinetic energy, for example. That
yeah.
is typically the case. So it's not so easy to find something that is satisfies every aspect. But again, I
So
think it's worth pursuing, and they're doing it.
Yeah.
So,
chasing the
so
CMP
my
with
question
ghosts.
was, do we expect some surprises on the structure formation front with relativistic Mond, which might address some of the problems pointed out by
Well,
your.
I would call it relativistic Mond because Mond, as you know, is just an empirical form, right? You're talking about some relativistic theory that will yield Mond in the low
Yeah,
energy
yeah,
level.
yeah.
Yeah,
I
yeah,
mean,
that's what I
Yes.
mean. Yeah.
my picture is a gauge theory, which is a fifth force, which is nicely matching with the standard model. That's what I would
Yeah, yeah,
go for.
yeah, yeah, yeah. So that has proved elusive. So in particular for Teves, it turned out actually that the vector field actually had much more influence than the tensor, which this was not initially recognized and so on. Again, I think I'll go back to what I said earlier. I don't think enough attention has been given to the problem. There are a few people like Scottis and
Yeah,
others who are pursuing it, but the bulk of the community likes to just jump on them whenever they try to publish something and say this is ruled
yeah,
out. And so we don't, I mean, I think the honest answer is we don't, I can't answer your question. There's not enough
yeah.
known about the problem, right? It has not been discussed
Igor,
sufficiently.
Igor has a comment.
Yeah.
Our paper shows that MON can be understood as a consequence of quantum corrections to GR. Yeah, this is what Igor talked about. Yes.
Okay, I didn't know that. I mean, I knew of Tevez, of Bekenstein. That's
One thing also I forgot to ask. This we heard of the so-called axis of evil in the CMB. Can you say what is its status today? Is it gone now, or is I'm particularly interested in a universe which has a preferred spatial direction. All the three directions are not um, identical. There is a preferred direction. Some of the work we do suggests that. So, could you please comment on something like that? Yeah.
So these Bianchi models they have, I mean, you don't have just one scale factor. You have got, you can have different scale factors, and there could be a preferred direction. Axis of evil, if I, so with CMB, there are different anomalies people have been talking about. There is the cold spot that people have been talking about, that was considered an anomaly. I don't know where it is now. I think it's probably lingering is still there. And then there is the asymmetry in the fluctuations, but this asymmetry is not really aligned with what we are seeing actually. So I think the directions are different.
I see.
Then there was this another anomaly that George Stasiou was talking about a lot, which is what was it, Subir? You know this much better than me. So there were different anomalies, right? There was this, and then all of them more or less in the same direction, and that was the axis of evil people were referring to.
It was the quadruple octuple alignment, but that seems to be something to do with the ecliptic, and that is unlikely to be cosmological. That was the feeling. But yes, there are indications in the CMB, but those don't appear to be related to what we find, because in fact, if anything, it's exactly at right angles. It could be, but we don't know that yet. As I said, these are all good questions, but we really need sound data to address them. But it's good to formulate the questions now, so when the data comes, we would be ready to look at it. But most of all, we need more hands on the job. Okay, that's what I'm saying.
More young people
more people to look at the data. I just fail to understand why something as exciting as this is just ignored by, I don't know. Never mind.
Roya, could you kindly stop sharing so that we see each other on the full screen?
I'm sorry.
Yeah, no, don't be sorry. It's just, we do this customarily in the end so that we have the full screen to see whoever is left. Yeah, great. Thanks so much for I mean, this is memorable. And yeah, I didn't read all the comments on the chat, but I think it will be there in the recording. Igor, you have something to add? I think I missed some of your comments. You're muted, Igor. You're muted.
I've got a copy of all the chats, so if anything, I can.
Okay.
I hesitate a little bit because it is talk about observational cosmology, not about theoretical physics. But I just wanted to pay attention to our paper, which is just accepted, that we are able now to estimate the cosmological constant based on a different approach to quantum gravity than for example, quantum gravity or string theory. And we get result which is within several orders of magnitude of error close to the observable value, and remarkably it is related to the scale of the so-called mass gap in the standard model, in the Young-Mills sector of the standard model. And also we are naturally explaining why the cosmological constant is related to the square of the Milgromian acceleration, and explain the origin of the scale of Milgromian acceleration, including its numerical value estimation of its numerical value within several orders of magnitudes of error because of the approximations used and uncertainties in the value of the mass gap itself based on the phenomenology. Okay, so I think that's enough for this.
Thank you, Igor. We are now finishing our time, and so again, a big thanks to you, Roya, for tolerating us for 2 hours here.
Thank you very much for the invitation. I really enjoyed it.
Yeah, great. So we'll see you all next on June 20th. Bob Cocker will talk on from quantum mechanics in pictures to quantum AI. So we shift to a different topic, yes.
Excellent. Thank you very much. Thanks, everyone.